Hi everyone online and people here. I'm super happy to present today on the speaker for the Breakfast Science seminar, the last one of the year. Today is Antoine Lutti, the senior lecturer of the CHUV-UNIL on the Laboratory of Research of Neuroimaging. So Antoine science trip start in New Zealand. Yeah, he did a PhD in MRI physics, and that I have to read because it's the development of diffusion measurements technique for the study of liquid crystals under shear.
So proper physics.
Proper physics.
No,
Like, he then moved to MRI in 2007 in UCL in London, where he did mainly develop acquisition sequences system for neuroscience, and he did a 3D EPI and multi-echo sequences for has ball sensitivity and MRI. He worked also in relaxometry and in B1 field mapping. He then joined Lausanne, the Laboratory for Research in in 2016, where he's now a technical director on the research dedicated MRI platform. His main research is focused on microstructural models and mainly relaxometry. So the floor is yours, Antoine. Looking forward.
Good morning, everyone. Thanks for having me. And so, like she said, like Elder said, I work mostly on relaxometry, and that's what I'm going to be talking about for the last half an hour. But to kick things off, I'd like to say a few words about brain loss, which is a brain imaging study that's been going on for the last 10 years at the hospital. So it's part of a larger longitudinal study that you might have heard about. It's called CHUV-UNIL, and it's a study of the local Lausanne population that's been running since 2003. So it started off as a study of the prospective study of the risk factors associated with cardiovascular and psychiatric diseases, and then over the years, there were like a number of sub-studies that sort of got involved as well to study other factors like sleep disorders, environmental factors, gender, education, and the rest of it. So we joined that study in 2014, and basically brain loss is the sort of brain imaging arm of the CHUV study. And I think the cohort is remarkable in several ways. I mean, there are other large-scale sort of brain imaging cohorts worldwide, obviously, but this one has a few very interesting sides, I think. First of all, is the time span of the longitudinal studies, right? So we've been going since 2014, so that's 10 years, which is quite an achievement. And over that 10-year period, so the participants have been coming at regular intervals plus 4 time points. So it's quite extensive. We've got 2,000 plus participants. Unfortunately, we don't have all participants for all time points, so it's all a bit jittered, but it still is a fairly extensive data set that covers a really and it's also special in terms of the data that we acquired and that we still acquire, although things are ramping down now. But so in terms of the data that we acquired, so it's mostly a data that's acquired with custom-made pulse sequences tailored for neuroscience, and I hope over the course of that talk you'll get to appreciate why that is useful. So it involves relaxometry, which I'll be talking about mostly today, but also diffusion, function imaging, and as well as the structural, the usual structural scans. So like I said, mostly I'll be focusing on the relaxometry today. So I'm going to show you some of the stuff that we did, developed, and learned over the course of doing this. I'm a methods person, so I'm not going to show you any neuroscience results, really. I'll just do the methods part, really. Yeah. So in passing, just a few words about relaxometry for those of you that might not know about it. So relaxometry is about estimating the values of the MR parameters that drive signal intensities. T2, T1, T2 star, magnetic susceptibility, magnetization, transfer. There's a whole range of them. Okay, and the beauty of that data is that the value of the estimates at each pixel is a reflection of what's happening inside the tissue at the microscopic level. Okay, and that is a way to probe the microstructure of brain tissue from live individuals. So I'm showing a couple of examples of this here. On the left-hand side, you can see, if you sample maps of the parameter T1 or R1 halfway across the cortical area, the areas that really light up are primary cortical areas like motor, auditory, V1, MC. Okay, these are exactly the regions that show the highest level of myelin density, as shown in ex vivo histology. So it's a way to show how we can use that data to probe and investigate myelination change in vivo. Another one on the right-hand side here is the correlate between iron concentration within brain tissue and R2 star. I can see the nice ribbon of high iron concentration along the cortical ribbon here that shows into a higher R2 star values. So relaxometry data is a way to investigate macrostructural change in vivo, right? And because that data is so close to the tissue, it's been used quite extensively for a range of neuroscience applications, starting with brain development, everything that's got to do with myelination change typically, and also the corresponding brain disorders like developmental delays, or autism spectrum disorder, or ADHD, or even Down syndrome. We've got a very nice study on this that came out a couple of years ago. Another typical example is MS. That's really used extensively in order to investigate everything that's got to do with a sort of demyelination, remyelination processes that take place. And an interesting one is also Alzheimer, and I think that's quite nice here. If you look at the current literature in an Alzheimer's disease, I think one of the unknown points is if you take a set of brains that are pathologically proven to be affected by the disease, considering the aggregation of beta amyloids or tau proteins typically, these brains might come from patients that will have shown symptoms, or typically, cognitive loss, and other brains won't, from patients that didn't. Okay, so why is it that the brains of some patients will lead to cognitive loss and others not? And it turns out iron has to say in this. Typically, it's the iron concentration that determines patients will ultimately develop symptoms or not. And from MRI markers of iron at baseline, you can predict in the future what patients will develop cognitive symptoms or not. So it's a very nice way, a very useful way to get an insight into the sort of pathophysiological process underlying brain disease. So, and in the context of a longitudinal study, I think it's a very general idea, but particularly in the context of a longitudinal study, I think it's because the data is so close to the tissue, it is particularly suitable when you're trying to look for early detection of brain disease. And in order to sort of illustrate my purpose, I'll consider the case of lesions. So most often, I think lesions are analyzed using macroscopic sort of morphological measures of the lesions. Yeah. So iron load measures like number of lesions, lesion size, and things. Right. So it's really morphological and macroscopic. Now the thing is, if you consider the voxels that appear normal just around the lesions, well, these voxels are already showing changes in the values of the MRI parameters. So there's something happening there in the normally appearing white matter that you can pick up with the relaxometry data, but is not sufficiently strong to sort of show the usual lesion feature. Okay, so it's a different approach to the dealing with lesions in general. And I think that there really is a promising future. And I think that the approach to this is typically on the model of what's been done for multiple sclerosis, where you basically define normative values of, say, T1 in that case, okay, across a healthy population. And then you deal with individual patient data by considering a deviation from these normative values using their scores typically. And that's a way to pick up a change in T1 in that case that you wouldn't see using standard lesion detection methods. Now, the other, I think, value of relaxometry for early detection of brain changes I think it becomes apparent if you consider disease evolution. So I've taken the example of Parkinson's disease here. So like other neurodegenerative diseases, typically Parkinson's starts off, at the level of the brain pathology, maybe 10 or 20 years prior to clinical diagnosis, right? So you've got the prodromal phase, you've got patients experience REM sleep disorders, and in terms of the pathology, you've got accumulation of alpha-synuclein that are magnetic aggregates. Okay, gradually over time, there's lots of dopaminergic neurons, and with an increase in iron concentration. So you can pick these up quite clearly with suitable relaxometry markers like magnetic susceptibility over to time. Okay, but then morphological measures of the brain cortical thickness, volume, and the likes, these only become relevant a lot later over the course of disease evolution, right? So you're just in a better place to pick up early changes in the brain due to brain disease. And I think you could make the same considerations regarding Alzheimer's disease as well. So here we are. That is for the sort of the overall. So one word to keep in mind is if you consider cross-sectional and longitudinal change, one I think fact that we should be aware of is that in the longitudinal studies you might expect the effect size to be a lot smaller in general. Okay, so I'm showing here an example of a change in magnetic susceptibility over a broad age span of 60 years on the left. And then on the right, you've got magnetic susceptibility increase over a 3-year period in a longitudinal study, right? And the effect size is roughly 1 order of magnitude smaller in the longitudinal study. Okay, so it's very small. There's a lot of advantages in doing it, but the effect sizes are very small in general, I think. So if you want to give yourself the best chances at detecting an effect, I think you want to have tailored acquisition and analysis strategies that will optimize sensitivity. Okay, and at the end of the day, so what that means is basically you want to reduce the noise level as much as possible. Okay, and with the remaining noise level, what you want to do is to make sure that the noise level is uniform across data sets. And making the noise level uniform across data set is something that's called harmonization of data, okay? And is typically done in the context of longitudinal or multi-center studies. Okay, so you've got data coming in from site A, site B, different time points and the like. And harmonization involves modeling for non-uniform variance. Okay, so exactly like I said, time point, site, scanner, hardware, software, protocols, and stuff like that. Okay, so softwares like Combat or longitudinal Combat do that really well. Now, these confounding factors, they're all categorical variables, like binary, 1 and 0 sort of thing. Okay, so you have a large data set, and what you effectively do is you bend the data into different subgroups, yeah, and you're trying to model the differences between the groups, right? But if you think about it, there's a whole range of other confounding factors. Take scanner environment, for example, or head movement that play a role as well. Okay, we know, the humidity around the scanner platform has an impact on temporal stability. A classic one is head movement. We all know that head movement leads to a degradation of image quality, which leads to an increase in the noise level. Okay, so these factors, they're also very important. They're not accounted for well in the literature. And I think they differ from the usual factors for 2 reasons. One of them is that they are continuous variables. If you're able to quantify data quality, it will vary along a spectrum. They are not binary variables anymore. And the second point is they work at the individual level of one data set, not different subset or subgroups of the overall data. So you need to work on harmonizing the data at the level of each individual image, if you like, if that makes sense. Yeah, that's not done well, but we've been working on this. So when it comes to harmonization of data in general, there are 2 ways of going about this. One is the retrospective strategy, right? So here is your analysis data. most of it will probably be fine in terms of motion artifacts, okay? But you'll be, you'll have some of the, not so good ones and a few really bad ones, okay? Now, at the level of an analysis, you want to be able to predict from the data and the data degradation, how much is going to impact the noise level in the analysis. So you want to have a model on how image degradation leads to increase in the noise level, to account for it at the level of the analysis. And the second strategy is to do this prospectively. So design tailored acquisition strategies that allow you to decrease the noise level in the data you acquired so that you don't need to deal with it at the analysis stage. So we'll consider an example of both strategies. So I'll take the example of motion degradation, which is a notorious problem. Okay, so what you want to do here is retrospectively account for a non-uniform image quality across a data set. Okay, so how do you go about modeling the effect of motion artifacts on an analysis? So the step number one is to have available a reliable index of motion degradation. Okay, how badly affected is the data by head motion? Okay, so it's an index that is derived from the image itself, and in order to have to use it reliably, you need to be confident that you have the marker is indeed a direct reflection of the motion history that took place during the acquisition of the data. So you want to have a relationship like this in some shape or form, okay, which is difficult to get by. Most people don't have it, okay. Now, so if you do have that index available, well, then you can compute it individually for each image of your data set, and you pull that histogram, and this is what you get. Okay, so typically a low motion degradation index will reflect good high image quality data, and you get a few odd ones that are very, very poor. Okay, now starting from there, I think what people would normally do is, okay, how do you go about this? Well, you define a threshold. Okay, and then you just discard all data sets above a threshold value, just exclude it from the analysis. Okay, and I think that is problematic in two ways. One, because defining objectively that threshold might be difficult. Okay, and second of all, because the chances are, if you studying children, non-compliant patients, Parkinson's patients, or something like this, the chances are that the data of interest in the analysis will probably be the one that is the most affected. Okay, so instead of a crude binary decision on whether to include or exclude the data, you want to come up with a more continuous, smooth process. And so that's what we've done for relaxometry data. We've called it quickie for quantitative imaging, analysis of quantitative imaging data using a quality index. So you start off from these values of the motion degradation index, and you use restricted maximum likelihood to model the noise in the data as a function of the quality index. And that allows you to compute a noise covariance estimate, so an estimate of the noise level in each individual image that depends on the value of the motion degradation, the level of the noise that is attributable to the head motion. And from there, it's fairly straightforward to compute weights that are as the inverse of the noise covariance matrix. And that histogram here is basically it's a distribution of the weights that sort of continuously account for the level of data quality. Right? So that allows you to move away from that binary inclusion-exclusion threshold. So now you've got your data, you've got two ways of analyzing it. So in the situation of a standard TLM analysis, so you've got the sort of ordinary least square approach, which consists in estimating the betas and running statistical analyses. Now, if you do this, what will typically happen is you'll see that there's a very strong increase in the noise in the data with the motion degradation index. So this relationship here on the top right is the equivalent of these plots of noise versus site or scan type in the multi-center analysis that the relevant papers show. Okay, and this is not good news in terms of statistical analysis. It's called heteroscedasticity, and that jeopardizes the validity of statistical tests. Instead, you can use the weights that were computed with Rameau, okay, in order to exactly sort of downweigh continuously the worst affected data in order to restore homoscedasticity. And that way it allows you to use all the data sets available. Okay, so we've done analysis of, comparative analysis of sensitivity between the standard ordinary least square approaches and weighted least squares. And what you find, using F-scores over age-related changes in the data as a measure of sensitivity, that you find that weighted least square analysis typically yields higher sensitivity than the usual OS, because you've been able to fine-tune the weight individually for each data set based on their image quality. And it also does a better job at restoring homoscedasticity than simply inserting the motion degradation index in the design matrix. And that's something that's been reported in other studies as well. Right, so here we just talked about, handling non-uniform noise retrospectively, okay? And that requires having a suitable index, okay? Now, there will be cases where having a suitable index might be challenging. So consider physiological noise, for example. It is a lot harder to get an index of cardiac-induced noise in our case, or respiratory noise in the data than it is than motion-related quality, right? So there will be cases where having such an index is really difficult. In that case, the alternative is to act prospectively, okay? We're going to tailor acquisition strategies designed to mitigate that particular source of noise in the data. So I'm showing here a movie of the changes in R2 star across the cardiac cycle. So that movie was computed from 5-dimensional data sets of the signal change over the cardiac cycle, yeah? And the R2 star were computed separately for each cardiac beat, right? And what you're seeing here is that roughly there are sort of up to 15% changes in R2 star across the cardiac cycle, okay? And primarily in inferior brain regions like the brainstem or the cerebellum, okay? And in terms of neuroscience studies, that is not good news, because that's an additional source of noise that will contribute to variability and sensitivity loss in a neuroscience study where you're looking at brain tissue change, right? So from there, we established a complete fingerprint of cardiac-induced noise in the data to look at sort of case-based coverage, amplitude, timing relative to the cardiac cycle, and things like this. And from there, we designed based on the fingerprint of cardiac-induced noise, we designed suitable strategies to mitigate the effect. So the bottom left images here show maps of the variability of R2 star across multiple repeats for standard acquisitions, and for an acquisition scheme that is optimized to mitigate cardiac-induced noise. Right? You can see with the standardly acquired data, you've got particularly high variability of R2 star across repetitions in inferior brain regions. But with suitable optimal acquisition schemes, that variability is gone. Okay, you've got variability that is a lot more spatially uniform and reduced. And we find that typically those techniques, they allow to reduce the variability of R2 star by up to 25% for R2 star maps and quantitative susceptibility maps. So it's really a substantial improvement. Now, for those of you in the room that might be familiar with sort of case-based and the principles of image encoding, I'm going to have a little geeky moment to sort of give us I think there's some really insightful physics in that, which I think is quite interesting. So if you consider the way data is typically sampled in multi-echo gradient data. So typically, you start off with an RF excitation, you sit somewhere in K-space, and then you just acquire all the multi-echo data consecutively, but at this particular K-space location, right? And then next repeat, you just move to another K-space location, and again, you acquire all the multi-echo data consecutively. So you move sort of vertically in that 2D KTE space, okay? And because cardiac pulsation leads to an apparent change in R2 star, if you acquire the data at a certain phase of the cardiac cycle or another, you're going to get a different transverse relaxation rate. This is what happens. That's what it means. Okay? Now, the simple way to deal with this is instead of traversing sort of KTE space vertically, you just change K-space location between consecutive echoes. So you traverse that 2D space diagonally. Okay? And if you consider one K-space location now, that vertical box here, it's made up of multi-echo data points that are acquired at different cardiac phases. Okay, so that effectively, when you compute the R2 star estimation, it basically leads to an average across the cardiac cycle. That's where the averaging comes from, right? The improvement in stability comes from. And there's also another neat observation is that, so it's got to do with spatial aliasing. Okay, so spatial aliasing in an image is something to do with, point-to-point change in K-space, okay? Now, in the case of a standardly acquired data, you see the change in the cardiac phase between consecutive K-space points here is the same for all echoes, okay? And that difference in the cardiac phase at which you acquire the data, ultimately it's what will determine the spatial aliasing of a pulsating effect. And that remains the same for all echo images, okay? So you're gonna have spatial aliasing in your R2 star map or in your QSM, okay? But here, if you sort of tweak your sampling skew and move diagonally, the changes of the cardiac phase at which you acquire the data between consecutive points changes from one echo image to another. Okay? It's not the same anymore. And that means the spatial aliasing won't be the same either. And if you do the R2 star fitting, well, typically the spatial aliasing tends to average out. So I'm showing a couple of examples of this here, where on the top left, I can't see my pointer. Yeah. Okay. But anyway, so if you on the top left here, you're seeing an example R2 star map around the hippocampus. And you can see here with the optimized sequence how well you can delineate the cortical layers really quite accurately all the way. And there's just no way to do this. Data is acquired in a standard way, right? You could, I think appreciate the difference in how crisp the data is on the sagittal view as well. It's also really clearly apparent if you consider the brainstem, which we know is affected by pulsation and pulsation effect is called it, right? So you start off with standardly acquired data where it's all a bit really messy, and if you mitigate these effects, the data is a lot more crisp, and the contrast is also a lot better. You can really tell how blood vessels, white matter, and grey matter, and everything. So it has that nice additional benefit on top of just improving sensitivity. And then to finish, so we've put all that work into improving data quality, reducing noise, and all the rest, physiology, morphine, and everything. And the question is, okay, what's that? What for? Okay, so I want to show you an example of what you can do if you if you try and get as good data as possible. And the application I'd like to talk about is how to characterize ion distribution in the subcortical grey matter. So, broadly speaking, I think so transverse relaxation decay is expected to follow an exponential form, okay? And it turns out that, however, so theoretical studies have expect that in the presence of magnetic material distributed within the tissue, that the decay of the signal should follow a non-exponential behavior, where the Gaussian shape at onset at short echo times and a transition to exponential at longer times. And that was never reported in experimentally. And because now we've got so much more sensitivity and reduced the noise level, we can really reliably pick it up. Right? So they say this is exactly the sort of transition from a Gaussian behavior at short echo times, and then to the exponential decay rate at later echo times. So having data with reduced noise on it helps you pick up very small effects in the data, and that means because at signal behavior, instead of one R2 star map, you have maps of 2 MR parameters. Typically, they tend to show very similar patterns between regions, with high values, typically iron-rich regions like the Palladium or the substantial Niagara. I mean, okay, the map of omega squared is obviously more noisy because the effects are so small, right? So from there, I mean, you could argue, well, if both maps sort of show the same effect, but it really is the point. But the point is that now you've got at hand, you've got a set of 2 parameters instead of 1, and you can try and characterize the underlying distribution of the magnetic material within the tissue. There are models around on how the MRI parameters should depend on the relevant histological properties of the brain. Right? Typically, the main parameters of interest are the volume fraction of the magnetic material, in our case, unreached cells. So it's how much of the space is taken up by these inclusions, and the intracellular ion concentration. So how much ion is located within the cells themselves, right? Not a bulk measure of ion concentration. It's really intracellular. So you've got 2 MR parameters, 2 estimates, 2 properties, 2 estimates. So you might as well just have a go. And this is what it looks like. So it's obviously still very noisy because there's still a lot of work to be done. But the general observations from here is, the estimates that we're getting are reasonable. Okay, the volume fractions are in the order of a few percent, which is consistent with what the sort of histological findings, and so are the intracellular volume fraction estimates, which I think, if you come to think of it, it's a bit of a miracle. Huh? So particularly if you zoom in on the substantial Niagara, this is what the estimates of intracellular concentration looks like. And we end up with an average of 0.8 milligram per gram of body tissue of iron within the cells. Okay, and if you compare this with ex vivo measures of iron concentration, dopaminergic neurons, typically histological averages are around about 0.5. So it's not bad, it's pretty close, which I think is very encouraging. So I'm not going too much into the details of this now, but because I think it's really early days, there's a lot of work that needs to be done to improve this. But now you've got a way to measure of the tissue. I think the point here is really the specificity that we're talking about, properties of relevant tissue properties that you're able to characterize from in vivo data, right? And then you can sort of find applications of this for the study of brain disease, typically Parkinson's, for example. We know that early days, so we talk about, you have a loss of dopaminergic neurons, which are iron-rich in the brain, but accumulations of alpha-synucleins, which are also magnetic because they link with iron. And the good news is, so I won't go into the details, but we are seeing difference between healthy controls and early disease patients. So we are able to obviously pick up a difference between the cohort, between healthy and patients, but to the future will be about investigate what the corresponding histological changes are. So in a nutshell, I think imaging neuroscience involves a lot of different disciplines that need to work together nicely in order to get to a successful outcome. So these are the nature, the brain markers that are used in neuroscience studies. There's a lot of work that needs to be done to optimize data quality and the suitability for applications in neuroscience, data analysis. All of these things, they need to work together to lead to a successful neuroscience outcome. And to conclude, I'd like to thank the people who actually did the work, for the most part, Quentin and Rita, as well as everyone else involved.